Alright kiddos, this one might seem a little bit longer. This is vodcast 3.3, molar mass and molar volume. Slightly longer than normal, but this is like a really super massive important topic. And I know that I say that about a lot of these topics, but what makes this so important is that you're going to be doing this all year long in almost every calculation from here on out. So, we're going to talk about how to find the mass of something that's a compound. So in yesterday's or the day before stuff, we just did an element. So you looked up the gram atomic mass on the periodic table and you wrote down that many grams equaled 1 mole. Well, what we're going to do today is, most of the time we're not dealing with a single element. Most of the time we're dealing with compounds. And so in this case we had SO3. So I'm going to look for sulfur. Okay, so 39 or 32.07 or 32.06, and oxygen, which is 16.0 once you round everything up. And we're going to go back and we're going to plug that in here. So I've got 1 sulfur, S, 1 sulfur. O3 means 3 oxygens. Okay, so I plug in the gram atomic mass from the periodic table. Again, these numbers are from the periodic table. And we multiply by however many of them we have, so 1 times the 32 for sulfur, 3 times the 16 for oxygen, and then we add them up. So in this case we get 80.06 grams of SO3 equals 1 mole. You see the way that I wrote it right here, that's grams per mole. That's how you would write it if you didn't put it in an equality. Okay, if we want it in an equality, we're then just going to write it like this. So 1 mole of SO3 equals 80.06 grams. And we would use that then as our conversion factor. Okay, now, definition-wise, this is what we call the gram molecular mass or the gram formula mass, depending on whether it's ionic or molecular. You don't know that at this point, and that's okay. Most of the time, though, we're going to call it this. We're going to call it the molar mass of the whole thing. That is what is super important. In fact, we're going to call what we did yesterday the molar mass as well, the gram atomic mass. That's the molar mass. If we're trying to find how much mass 1 mole has, it's always the molar mass. Okay, and it's always so many grams equals 1 mole. And remember, at this point, everything is equal to 1 mole. Okay, so we're going to run through a few of these just to see how easy they are to calculate. So for carbon dioxide, we've got 1 carbon, we've got 2 oxygens. We look up their mass on the periodic table. Okay, so carbon is 12.01. Usually I just use 12.0, but 12.01 is certainly okay. And then oxygen we know is 16. We've worked with that a couple times. And after a while, you'll start to sort of memorize these. You'll just know them because you've worked with them so much. So 12.01. Okay, so 1 times that, 2 times 16. Remember not to accidentally multiply that by 20. Okay, it's 2 oxygens times 16. So 12.01 plus 32. Okay, and that's going to give us 44.01 grams. And remember that equals 1 mole. So 1 mole of carbon dioxide equals 44.01 grams of carbon dioxide. Okay, and once you've got that, then these work out the same way as what we did yesterday with gram atomic mass. You just plug them in as conversion factors. All right, so let's work the next one. This is number 9 on your sheet. So hydrogen is 1. Okay, sulfur we've done before, but I looked it up again. It's 32.06. Oxygen, we got 4 of them. So 2 hydrogens, 1 sulfur, 4 oxygens. Okay, we're going to multiply those out. We got 2 for hydrogen, 32.06 for sulfur. And then we're going to get 64 for oxygen. We add all those up. We're going to get 98.06 grams, okay, of H2SO4, which is sulfuric acid. We'll learn that a little bit later. Okay, and that is equal to 1 mole of sulfuric acid. Okay, so nice little qualities, and if you write them like this, again, you can write them as grams per mole, but if you want to do conversions with them, it's easier if you just go ahead and write them this way. Okay, and that way you've got an equality already set up. Conversion factor is easy. Okay, so number 10 presents a little problem. So 3 irons, no problem. When you see a number outside of parentheses, you're going to treat this just like you would in algebra. You're going to distribute that 2, so it's 2 times 1 for phosphorus, so that's 2p, and then 2 times 4 for oxygen, okay, which is going to give us 8 oxygens. I jumped over here so you can see iron 55.85, phosphorus 30.97, okay, and this is ptable.com. Super useful website, okay. So we've got those, and those should all be times, not equals. Sorry about that. I think I'm going to fix that here in a second. So iron's 55.85, phosphorus is 30.97, oxygen, of course, is 16. And most of the time we can kind of do some of these in our head, but I'm probably going to need a calculator for these. So 3 times 55.85 is going to give us 167.55, I think. Okay, so 167.55, I believe. 2 phosphorus. Okay, so we're going to end up with 61.94. And then 8 oxygen, so 8 times 16, that's going to give us 128. We're going to add all those up. So much bigger molar mass than we've typically had, but there's a lot more atoms in this. Okay, so that kind of makes pretty good sense. 357.49 grams equals 1 mole. Remember, always, always, always 1 mole at this point. Okay, it's always good to label it. Okay, Fe3PO42. And there should be an equal sign here. Sorry that I missed out on that somehow. Okay, so let's use those. Now, we use these the same way that we used everything for gram atomic mass in the last lesson. It just gives us the conversion factor. So molar mass is how you find the conversion factor that you're going to use when you're dealing with a compound. So CO2, okay, we've already calculated that one in the previous slide, but we'll go ahead and do it again just to make sure. So 1 carbon times 12.01, 2 oxygens times 16.0, okay? And that's going to give us 44.01 grams of CO2, 1 mole of CO2. That's what we found back in number 8 if you look on your sheet. But it's okay to calculate it again. There'll be times where you won't remember it, so you need to do that. And our given in this case is 66.0 grams of CO2, and we're looking for moles. Okay, so that's our unknown, moles of CO2. And it's really pretty straightforward. This works just like gram atomic mass, and we got one conversion factor. We're just going from grams to moles. So my given, 66.0 grams of CO2. On the bottom is going to be 44.01 grams of CO2. And then the other half of that, 1 mole of CO2. Okay? Punch that in your calculator. Don't even really need a calculator for this one. You can kind of do it in your head. 3 sig figs, 1.50 moles of CO2. You probably got 1.5. Okay? But you need 3 sig figs. So if you need more and you're after the decimal anyway, just tack a 0 on the end, and that will give you that additional sig fig that you need. Okay, now, number 12. Number 12 can be tricky. Okay, so I want you to read that problem. Okay, if you need to, pause it real quick and read through the problem before you do anything else. Okay, our given here, 0.0500 moles of hexane. Now, if it's something that you don't know how to find the formula right now, since we haven't talked about naming, I'll give you the formula, and it's there, C6H14. I'm looking for number of molecules. Okay, number of molecules. So, as soon as you see molecules, you should immediately jump to Avogadro's number, just like atoms. So 1 mole, 6.022 times 10 to the 23rd molecules. Okay, so that's not too hard. And then what we would typically think is, okay, I need to find my molar mass, particularly since we've just been working all these problems with molar mass. So I start to work that out. 6 carbons times 12, 14 hydrogens times 1. Uh-oh, wait a minute. Why am I doing this? Okay, I don't actually need all this stuff. Okay, I'm going to go ahead and finish calculating it out just so you can get a little bit more molar mass practice. 86.06 grams equals 1 mole. Okay, of hexane, C6H14. But here's the deal. I don't need it. Okay, and in fact, if I try to use this, my problem is going to be wrong because there's no grams in this problem. Okay, it doesn't ask for grams, it doesn't give me grams, there's nothing about mass or anything like that. Okay, so what that means is when I go to set up my boxes and my conversion factor, I put my given in, okay, 0.0500 moles of hexane. I think I tried to squeeze that in here. And I'm going from moles to molecules, so I just need this. Okay, I just need Avogadro's number. I didn't have to calculate this molar mass at all. It doesn't really hurt anything that I calculated it as long as I don't try to use it. Okay? If I tried to take this and somehow cram it into my railroad tracks, it's not going to cancel out. And that's why it's super important that you do make sure that you cancel out everything correctly. Because if you start throwing stuff in there that doesn't cancel, then you're going to be in bad shape. So just cross through that. You don't need it at all. Okay? And so I've got everything I need right here. Pretty simple, one of those easy multiply problems. Punch it out. We're going to get our correct answer here. So this is a case of be careful, don't use stuff that you don't need. Okay, one thing that sometimes we leave out a little bit, this is pretty simple, standard molar volume. Basically it means this, it all boils down to this. If we're talking about a gas is standard temperature and pressure, which is freezing, 0 degrees Celsius in 1 atmosphere. It is always this, that 22.4 liters equals 1 mole. It doesn't matter what gas it is, as long as it's a gas and it's at STP, then this is always true. Okay, so we look at our example, determine the volume in liters of 0.60 moles of sulfur dioxide gas at STP. So we're at STP, so this applies. Write down my given. I'm looking for liters. I'm just going to take this little conversion factor and throw it down here. 1 mole of sulfur dioxide, 22.4 liters on the top. Cancel what cancels, which is moles of sulfur dioxide. Left with liters. Just punch it in. 13.4 liters of sulfur dioxide. Pretty simple. Real straightforward. I know that's only one example of that, but it's that easy. Okay, it doesn't get any harder than that for the volume ones. Okay. Thanks again, guys. Did a great job. I think we're doing pretty good on this stuff, and keep up and make sure you're practicing.